This short lecture on rational functions is presented on behalf of the Independent Learning Center of SQU. It is presented by Gerald Wanjala from the Department of Mathematics and Statistics. A rational function is a function of the form Rx is equal to Px over Qx, where P and Q are polynomials. One of the simplest rational functions is the rational function Rx is equal to 1 over x. Other examples of rational functions are given down here. Part A, we have Rx is equal to x squared plus x minus 1 over x squared plus x minus 2. Part B, we have Sx is equal to x squared plus x minus 2 over x to the power 3 minus x squared plus x minus 1. And the last example is Ux is x to the power 3 minus x squared plus x minus 1 over x squared plus x minus 2. All these are rational functions written in the form P over Q, where P and Q are polynomials. The first example, we have that P is a polynomial of degree 2, and Q is also a polynomial of degree 2. In the second example, you have that P is a polynomial of degree 2, and Q is a polynomial of degree 3. And in the last example, we have that P is a polynomial of degree 3, and Q is a polynomial of degree 2. A straight line x is equal to a is called a vertical asymptote of the function y is equal to f of x if y goes to either plus or minus infinity as x approaches a either from the right or from the left. In this picture over here, we see that if the green curve is the graph of the function y is equal to f of x, then we have that as x goes to f from the right, y will go to plus infinity. For the black curve here, we see that as x goes to f from the left, y will go to plus infinity. For the yellow curve over here, we see that as x goes to f from the left, y will go to minus infinity. And for the blue curve over here, we see that as x goes to f from the right, y will go to minus infinity. If we consider the rational function y is equal to 1 over x, then we see that y goes to plus infinity as x goes to 0 from the right, and y goes to minus infinity as x goes to 0 from the left. So the line x is equal to 0 is a vertical asymptote of the function Rx is equal to 1 over x. If we have a line y is equal to b, then that line is said to be a horizontal asymptote of the function y is equal to f of x if y goes to b as x goes to either plus infinity or minus infinity. If we look at the diagram over here and consider the green curve, then we see that as x goes to plus infinity, y will go to b. And if we consider the black curve also, we see that as x goes to minus infinity, y will go to b. So the line y is equal to b is a horizontal asymptote of the function y is equal to f of x, whose graph is indicated here in green. It is also a horizontal asymptote of the function whose graph is indicated here in black. So again, if we look at the rational function Rx is equal to 1 over x, then we see that y goes to 0 as x goes to plus or minus infinity. Therefore, the line y is equal to 0 is a horizontal asymptote of the graph of the function y is equal to Rx. Let R be the rational function indicated over here. We have that Rx is p over q, where p is a polynomial of degree n and q is a polynomial of degree m. So Rx is a nx to the power n plus a n minus 1x to the power n minus 1 up to a1x plus a naught, and qx is bmx to the power m plus bm minus 1x to the power m minus 1 up to b1x plus b0. The vertical asymptotes of this rational function are the lines x is equal to a, where a is a 0 of the denominator. So to get the vertical asymptotes of this function here, you just get the zeros of the denominator. If a is a 0 of the denominator, then x is equal to a will be a vertical asymptote of the function Rx. The following facts will be useful in sketching graphs of rational functions. Fact number 1. If for this rational function over here, the degree of the numerator n is less than the degree of the denominator, which is m, then R has a horizontal asymptote y is equal to 0. Let me say that again. If n is less than m, where n is the degree of the numerator and m is the degree of the denominator, then R has horizontal asymptote y is equal to 0. If n is equal to m, if the degree of the numerator is equal to the degree of the denominator, then R has horizontal asymptote y is equal to an over bm. You divide the leading coefficient of the numerator by the leading coefficient of the denominator. If n is bigger than m, that is, if the degree of the numerator is bigger than the degree of the denominator, then R has no horizontal asymptote. Let's look at this example here. Let R be the rational function given by 2x squared plus x minus 1 over x squared plus x minus 2. Then R can be factored as we have it over here. We factor the denominator as x minus 1 times x plus 2. Then we see that the vertical asymptotes of R are the lines x is equal to 1 and x is equal to minus 2. These are just 1 and minus 2 are just the zeros of the denominator. So this will give us the vertical asymptote. So they are x is equal to 1 and x is equal to minus 2. The degree of the numerator is 2. The degree of the denominator is also 2. The leading coefficient of the numerator is 2. The leading coefficient of the denominator is 1. And so the horizontal asymptotes, the line y is equal to 2. How do we get this 2? Divide this 2 here, which is the leading coefficient of the numerator, by 1 here, which is the leading coefficient of the denominator. So we get the horizontal asymptote at the line y is equal to 2. We have another type of asymptote that we call the slant asymptote. If R is equal to P over Q is a rational function in which the degree of P is greater than the degree of Q by 1. So the degree of P is bigger than the degree of Q by only 1. Then we can use long division to show that R can be written in the form Rx is equal to AX plus B plus SX over QX, where the degree of S is less than the degree of Q, and A is not equal to 0. This means that Sx over Q of X will go to 0 as X goes plus or minus infinity, because the degree of S is less than the degree of Q. And this implies that the graph of y is equal to Rx will approach the line y is equal to Ax plus B as x goes to plus or minus infinity. Why? Because as x goes plus or minus infinity, Sx over Qx will go to 0. And therefore, R over here will go to Ax plus B as x goes to plus or minus infinity. The line y is equal to Ax plus B is called the slant asymptote of R. So let's consider this example where R is given by 2x to the power 3 minus x squared plus x minus 1 over x squared plus x minus 2. Then if we do long division, we see that if we divide 2x to the power 3 minus x squared plus 1 minus 1 by x squared plus x, then we see we get 2x minus 3, which is over here, and the remainder is 8x minus 7, which is over here. And therefore, we can write Rx as Rx is 2x minus 3 plus 8x minus 7 over x squared plus x minus 2. In this case, Sx is equal to 8x minus 7, and Qx is x squared plus x minus 2. So we see that the slant asymptote of R is the line y is equal to 2x minus 3, which we have got over here by long division. Asymptotes, whether vertical, horizontal, or slant, are important while sketching graphs of rational functions. You will find the following guidelines useful when graphing functions of the rational function Rx is equal to Px over Qx. The first thing that you have to do is factor both the numerator and the denominator. Factor P and also factor Q. Factor the numerator of the rational function and factor the denominator of the rational function. The second step is you find the x-intercepts by determining the zeros of the numerator P. So determine the zeros of the numerator P, and this will give you the x-intercepts. The y-intercept will be determined by getting the value of r at x equal to 0. So the y-intercept is the value of r at x equal to 0. Determine this value also. At the third step, the vertical asymptotes. You find the vertical asymptotes by determining the zeros of the denominator q, and then after doing that, you determine whether y goes to plus or minus infinity on each side of each vertical asymptote. So you look at each vertical asymptote, you determine whether as x goes to the vertical asymptote from the right or from the left, what happens to y? Does y go to plus or minus infinity? This is called the behavior of the graph near the vertical asymptote. This can be done by using test points. The fourth thing you have to do is to find the horizontal or the slant asymptote if they are there, using the procedure described earlier. Now, you either have a horizontal asymptote or you have a slant asymptote, but you cannot have both of them at the same time. Then after you have done all this, just sketch the graph using the information you obtained above, and you indicate clearly the intercepts and the asymptotes and the behavior near the vertical asymptotes. So to conclude this lecture, let's look at the following two examples. The first example is we are required to sketch the graph of the rational function Rx is 2x squared plus x minus 1 over x squared plus x minus 2. So step 1, we factor the rational function R as indicated here. We have the factors of the numerator as x plus 1 times 2x minus 1, and we have the factors of the denominator as x plus 2 into x minus 1. The x-intercepts are the points minus 1 and 1 over 2. The y-intercept is the point 1 over 2. The vertical asymptotes, which are the zeros of the denominator, are obtained from the zeros of the denominator are x is equal to minus 2 and x is equal to 1. So this table down here shows you the behavior near the vertical asymptote. How does the graph behave as x approaches the vertical asymptote? What happens to y? So we see as you go to minus 2 from the left, the sign of y over here is positive, and so y will go to positive infinity as you go to minus 2 from the left. How do you get this? You pick a test point on the left of minus 2. As you go to minus 2 from the right, y, the sign of y is minus. As you go to minus 2 from the right, the sign of y is minus. So that tells you that y goes to minus infinity as x goes to minus 2 from the right. How do you do that? You pick a test point from the right of minus 2 and see whether using that test point the sign of y is plus or minus. Similarly, as x goes to 1 from the left, the sign of y is minus, and therefore y goes to minus infinity, and as x goes to 1 from the right, the sign of y is plus, and so y goes to plus infinity as x goes to 1 from the right. The horizontal asymptote here is the line y is equal to 2, because the numerator is a polynomial of degree 2, the denominator is a polynomial of degree 2, the leading coefficient of the numerator is 2, the leading coefficient of the denominator is 1, so we divide 2 by 1 to get 2. The horizontal asymptote is the line y is equal to 2. So with this information here, you just sketch the graph of the function. First of all, you indicate the vertical asymptotes which are here, this one and this one. Then you indicate the horizontal asymptote, which is the line y is equal to over here. Then you put the x-intercepts, minus 1 and 1 over 2, which are over here. The y-intercept is also indicated over here, which is 1 over 2. So using this table here, we know that as you go to minus 2 from the left, y goes to plus infinity. So we have this portion of the graph here. We see that as you go to minus 2 from the right, y goes to minus infinity. So we have this portion of the graph here. As you go to 1 from the left, y goes to minus infinity. So we have this portion of the graph here. And as you go to 1 from the right, y goes to plus infinity. And so we have this portion of the graph over here. The next example is to sketch the graph of the rational function Rx is equal to x to the power 3 plus x squared plus x plus 1 over x squared plus x minus 2. Now we notice here that the degree of the numerator is 3, the degree of the denominator is 2. So the difference between these two degrees is 1. So this function has a slant asymptote. Okay, so we again follow the procedure before. 1 we factor, and the factors are over here. We find the x-intercepts. This time we have only one x-intercept, which is minus 1. We also find the y-intercept is minus 1 over 2. The vertical asymptotes, which are the zeros of the denominators, are x is equal to minus 2 and x is equal to 1. So again, this table here, we list the behavior near the vertical asymptote, as we did before using test points. When we apply longer division, we see that the slant asymptote is the line y is equal to x. So we put this information together. The vertical asymptotes are over here. X is equal to minus 2 and x is equal to 1. The slant asymptote is over here, which is the line y is equal to x. The x-intercept is over here, which is minus 1. The y-intercept is also over here, which is minus 1 over 2. Now we use the behavior near the vertical asymptote. So we see that as x goes to minus 2 from the left, y goes to minus infinity. So we have this portion of the graph here. We see that as x goes to minus 2 from the right, y goes to plus infinity. We have this portion of the graph over here. We see that as x goes to 1 from the left, y goes to minus infinity. So we have this portion of the graph over here. And finally, we see that as x goes to 1 from the right, y goes to plus infinity, and we have this portion of the graph over here, and this gives you the sketch of the graph of our rational function.